Hello, wonderful people. Welcome to Cosmology Talks. Today we have Keir Rogers, who is a postdoc at the Dunlop Institute for Astronomy and Astrophysics, and Vivian Poulin, who is a CNRS researcher at Montpellier University. Today they're talking about a paper they have showing a tension between Lyman-α measurements and the Planck CMB. This is sort of a new tension, but sort of not. There have been hints of Lyman-α tensions for a while, and specifically this tension is coming from the amplitude of matter-power spectrum, or inferred amplitude being a bit too small, which is very similar to the S8 tension at lower redshifts. Hopefully they'll go into some details about how it may or may not be related to the S8 tension as they go. This is obviously interesting because of the high significance. It's 5 sigma, which is where people start to pay attention. But there's also the possibility it might relate to the other tensions. And maybe most interestingly, it appears to have a ready-made solution that doesn't mess up anything else in cosmology, which is the gold standard to actually believing a tension. I'll let Keir and Vivian go into details about what these possible solutions are, and I'm keen to hear about that. Other than that, welcome Keir and Vivian. Do you want to start by telling us briefly about your paper?
Of course. So, as you said, what we did is we took the data from the eBOSS Lyman-α forest, and I think we started with motivation that we were interested in, you look at the S8 tension and possible solutions to it. What do other complementary data sets say? And so we wanted to look at what the Lyman-α forest data say and its relation to Planck. And it turns out that if you look at the parts of the matter-power spectrum in which the Lyman-α forest is constraining, that there is a significant tension. So we measure a 5 sigma tension between eBOSS Lyman-α forest data and Planck CMB. And then in the paper, we consider which pieces of new physics would reconcile these data sets. And as you said, you see a suppression in the amplitude, but in particular, you see running in the tilt of the power spectrum. And so we find that you can essentially entirely reconcile the data sets if you have some running in the primordial power spectrum, as you might expect. But we also find, interestingly, that if you have certain deviations from cold dark matter, so a contribution of ultralight axions or warm dark matter, that this can also reconcile the data.
And was it true what I said in the intro, that reconcile this data without messing anything else up? It's not that you need so much warm dark matter that it would have been seen elsewhere?
Yes, essentially, yeah. There's no way that it would mess up any other data sets. I think one particular avenue to explore is what would happen on much smaller scales than what we're probing with eBOSS. But the amount of suppression you see in eBOSS is of order 10%, and we have no reason to believe that we can't have that much suppression with the amount of small-scale structure data that we have at the moment.
And because it's only a subfraction of warm dark matter or ultralight dark matter, you're not kind of like messing up anything on larger scales or any sort of expansion history things. They all kind of just stay exactly the same.
No, exactly, yeah.
Exactly. And say this is really what's important, is to manage to keep the large scales unaffected while maneuvering around the small scales to get them down, essentially. Yeah.
So if people are thinking of this talk or the paper in 6 months and there are only 2 things they're able to remember, what would you want those 2 things to be?
That there is a significant tension between Lyman-α forest data and Planck, but in particular, this was largely missed before. And we think that happened because the way that the data were compared didn't capture the information content of the experiment. And so largely when people looked at the consistency between Lyman-α forest and Planck, they were looking at the standard ΛCDM parameters. And actually, when you project the information to the full 6-parameter model, first you have to use priors to break some of the degeneracies. But in particular, you're projecting into scales and redshifts where you're not directly constraining the model, and so your error bars inflate. And so if you look at the standard parameters, there is apparent consistency. And it's only when you look at a parameterization of the model that captures the information content that you see the tension. And so I think that has broader implications for how we assess consistency with other data sets, in particular the weak lensing experiments.
Was that just one, or?
I have a secondary point, which is that we do find a preference for phenomenological running. And a colleague pointed out to me that actually this has a long storied history. So if you go back to WMAP and SDSS1, there has consistently been a preference for some running in the power spectrum when you combine CMB and Lyman-α forest.
When you say people didn't previously notice this because they were sticking to the kind of lambda CDM parameters, is there or should there be any mild concern that, you know, if you interrogate data in enough different directions, eventually you'll accidentally see the noise and you'll see a 5 sigma tension?
I think it's a question of characterizing where the information in the experiment lies. And so, again, it's actually a long and storied history of showing. So part of the details of what we do is that we use a compression of the likelihood, which compresses all the information to these two parameters that you can demonstrate fully captures all the information for all the models that we consider. So I suppose it's the parameterization in which your signal to noise is largest for the models that we consider.
I would say that, in fact, using the exact same data already back in 2019, there had been papers talking about hints of tension, a paper by Nathalie Palanque de Labrouille and collaborators Julien Lesgourg, Niels Schoenberg and others that have looked at that. So they already saw that there was a preference for this running of the tilt of the spectrum that was a bit weaker than what we get. And I do think that it might boil down to the fact that we are using this compressed likelihood that is sharper in extracting the information compared to what they had been doing. But I think it's fair to say they could have written a paper with a stronger sense or a stronger tense, and people would have paid attention to it in a sense. They decided to be more conservative and combine data sets and show what sort of constraints they get on neutrino mass, and those are in fact fairly robust. There is no criticism, but I think there was already hints of that, and we're going a bit further here.
Let's go into why you did this. I think it's a high sigma tension, which gets everyone excited, but there may be other things that you want to go into in the details here as to why this is important and interesting in 2023.
You know, we talked about wanting to assess consistency between data sets, but also we want to look for hints of new physics. So I've put up 3, questions about new parts of the cosmological model that we think need answering. And these relate to the particular models that we end up constraining using the compressed likelihood. These big questions that, of course, we're always talking about in cosmology, like what are the initial conditions, which relates to the primordial power spectrum, what's the origin of neutrino masses, where we want to do things like measure the sum of the neutrino masses, and what is the fundamental nature of dark matter. And axions and warm dark matter each have their own motivation. And I think in a lot of the work both I and Vivian do, we're trying to constrain those models, but using all the data that we've collected, and then we're forced to confront the fact that we currently have under lambda CDM parameter tensions, not just the Hubble tension in the background cosmology, but also at the perturbation level between CMB and large-scale structure. And we've identified that, in fact, Lyman-α forest is also in tension with CMB data, as well as galaxy weak lensing and to some extent galaxy clustering data. And so, as I said earlier, part of this work was a follow-up to thinking about solutions to the S8 tension. So I think for your audience, they know the S8 tension very well. S8 is this parameter that measures the amplitude of density fluctuations around 8 megaparsec scales, and we measure smaller values in galaxy clustering, galaxy weak lensing experiments than what's inferred from CMB experiments. And something that me and Vivian have been talking about is whether solutions to this require scale-dependent or time-dependent deviations from the standard dark matter model. And something we wanted to think about was, well, if it's a scale-dependent solution, so in the last cosmology talk I gave, we talked about how ultralight axions can reconcile the data set essentially because they suppress power partially around 8 megaparsec scales. And so they lower the value of S8 but maintain consistency with CMB on large scales. But that means that you should see small scale suppression at early redshifts as well, if it is deriving from something like axions. Or Vivian, and he should talk more about this, has worked on models like decaying dark matter or interaction between the dark matter and dark energy sectors. That would leave a time-dependent suppression, and then you might expect earlier probes to be more consistent with a cold dark matter spectrum.
Yes, exactly. So yeah, to cut it short, there is really two sorts of category of solutions to this S8 functions. Beyond, of course, there's always the possibility of a systematic in the data or in the modeling. That's not out of the question at this, or even just a statistical fluctuation. But taking this at face value, assuming that it's some hint of new physics, there is sort of two possibilities. As Keir was saying, either something happened only on small scales and could have been imprinted already from the early universe, or given all the data that we have from, in particular, CMB lensing at very late time, it could still be that something happened even on large scales, but they must be limited to very late time. And adding an additional probe that probes intermediate redshift, I would say, like the Lyman-α, is going to be able to disentangle and test what category of solution is favored, let's say.
I guess the crucial part of that is that it's intermediate redshift at small scales, because CMB lensing is already intermediate redshift at large scales.
Yes. Sorry. Thank you for absolutely. You're perfectly right.
And the other thing that maybe people who watched Keir's earlier talk will know this already, but anyone else, you are talking about, when you say these masses of these axions, only a percentage of the dark matter being in that. It's because I guess a lot of these masses are ruled out being 100% of the dark matter, but not ruled out at being 5% or 10% or 1% or some other number.
Exactly. So these are very light axions, around 10 to the minus 25 electron volts. So their de Broglie wavelength is 10 megaparsecs. And so you clearly cannot suppress all the power below that scale. But as we showed, in fact, it seems to improve consistency if you have some fraction of these very light axions.
Cool, thanks. Let's get into the details then. What did you do in this specific paper? How did you extract this summary statistic, and how does it show 5 sigma? And then I guess the very interesting stuff, how do we know warm dark matter and axion dark matter can fix it?
The Lyman-α forest is an absorption feature we see in the spectra of high redshift quasars, high redshift galaxies called quasars. And what happens is that the light from the quasar, as it travels towards us, passes through clouds of neutral hydrogen gas, and that causes Lyman series absorption in the light of the background object. And that always happens at a certain rest wavelength, but those lines are continuously redshifted because of expansion. And what we end up seeing is this forest of lines where the position and the strength of the absorption is a mapping of the density of the neutral hydrogen gas along the line of sight to the quasar, and that in turn is a mapping of the density of the dark matter along the line of sight to the quasar. And so in particular, we have very high resolution of line of sight fluctuations in the dark matter, where spectral resolution equates to spatial resolution in the dark matter distribution along your skewer through the IGM. An important note is that when we measure this power spectrum, we're measuring the 1D flux power spectrum. So we're effectively integrating over modes transverse to the line of sight across the sky, and we're just building statistical power along the line of sight.
What's stopping one trying to reconstruct a 3D field and then doing the power spectrum on the 3D field? Or is the answer just that quasars are too sparse?
Yeah, it's essentially that you have so many more modes along the line of sight. Now, that's not to say that there are efforts to measure the 3D power spectrum from the forest. In fact, there was a paper recently, I think potentially looking at some of the early DESI data, where they've started to measure 3D power spectrum, but you won't be able to get to such high K simply because you have much less sampling in the sky. So we took the data from the eBOSS survey, so they collected around 200,000 high redshift quasars with detectable Lyman-α forest. And so they had these large sets of these absorption spectra. There's two parts to the analysis. There is a BAO analysis, which is separate, and then there's a power spectrum analysis where they measure the flux power spectrum. And so that's the data that I'm showing on the slide now. So that's correlations directly in the absorption of the Lyman-α forest as a function of wave number, which has these inverse velocity units because you're measuring the correlations in the space of the spectra. So you relate the wavelength to a velocity. And you see that they measure the power spectrum from about 0.001 to 0.02 inverse kilometers per second, and that equates to about 0.1 to 2 h over megaparsec, roughly a factor of 100 to convert the units. and from redshifts 2.2 to 4.6. And the key observation here is that the range of scales to which they're sensitive when they're probed in the IgM gas, so that's where the absorption is coming from, that's mostly sitting around mean cosmic density. And so it's much less affected by nonlinearities than other probes at equivalent scales. So for example, if you measure the galaxy power spectrum at such small scales, galaxies obviously sit at the peaks of the density field, and so they're highly nonlinear probes, whereas this is coming from roughly mean cosmic density. And so the overdensities are not that large, of order 10. And so you have a very clean probe of the linear matter power spectrum around scales of 1 h/megaparsec. And then the redshift range is before dark energy comes to dominate. So you're very much in the matter-dominated epoch, where the universe is Einstein de Sitter. And so that's what leads to the ability to do the massive compression that we exploit. And in fact, this compression has a long history going back to some of the first SDSS analyses. So I give this reference for McDonald et al. In 2000. And this plot is illustrating why this compression holds. So this is pulled from a paper that I did with others, and Joe Fontbera and his student Chris Pedersen, where we took linear matter power spectra. So if we start on the left, top left panel, we have linear matter power spectra for different values of neutrino mass. And you sort of see the effect of neutrinos is to suppress the small scale high K matter power spectrum. The blue band shows the range of scales to which eBOSS is sensitive. And what you can do is rescale each of these power spectra to have the same amplitude and spectral index at a pivot wave number of 1 h/megaparsec and redshift of 3. And that's the plot on the right. And the point here is that once you have extracted that information, the amplitude and tilt at that pivot, these power spectra become indistinguishable. And it's essentially a statement that the power spectra are power law across the range of scales and Einstein de Sitter across the range of redshifts that are relevant. And at the bottom, you show the equivalent for curvature in the power spectrum. And in particular, for the models that we consider, we check that this compression is valid for the ΛCDM, neutrino mass, primordial power spectrum running, and the dark matter models that we consider. So this here is the ratio of these power spectra after they've been rescaled, i.e. that they've been compressed, the compressed information is being extracted to the ΛCDM model, and the grey band shows an estimate of the uncertainty on the power spectrum from the eBOSS data. So the error in doing the compression is negligible compared to the statistical error in the data. Importantly, this only holds for these dark matter models, this only holds true when you have subdominant fractions. If you had too large a fraction, you'd have a very sharp cutoff, and this compression would not be valid. But we check explicitly that in the parameter space, in fact, we set an upper prior on the fraction to guarantee that we're always within this regime where the compression is valid. This plot, first I highlight the black point, so that shows the measurement. So at the top I'm showing linear matter power spectra, it's a function of wave number k. The bottom is the ratio to ΛCDM. The black point shows the measurement from eBOSS. So this is as measured by the eBOSS collaboration. And so the vertical error bar shows the uncertainty on the amplitude at this pivot wave number. And so the blue line is the best fit ΛCDM model given Planck data. You see that it's partially suppressed, but not actually, the suppression by itself is not significant. It's around sort of 1 to 2 sigma suppression. And then the black band shows the best fit and the 1 sigma uncertainty on the spectral index. And so in particular, when you account for the running in the spectral index, the increase as you go to smaller scales, and you compare it to the Planck expectation, that's where you get this measurement of a 4.9 sigma tension between Planck and eBOSS. And I think this plot partly explains conceptually why when you project to standard ΛCDM parameters, the tension is weakened. So the light grey area shows the range of wave numbers to which Planck is sensitive, approximately. And so if you project the information that eBOSS measures to these larger scales, which sigma 8 is sensitive to, then essentially your error bar expands. And so you can appear to have consistency if you look at scales where your information is being diluted, but it's only when you look at the actual scales to which you are sensitive that the discrepancy becomes clear.
Hi, me from the editing table here. There was something that really confused me about this result during the recording. And I tried to articulate it in some questions, but at the time it wasn't fully clear to me what I was confused about. So Keir and Vivian did their best to answer my questions, but I was ultimately left confused. However, I think others might have a similar confusion, so I'll try to again to articulate it now. Thankfully, I also understand the resolution now, so I will articulate that too. My confusion essentially lies in this figure and how the amplitude can be so uncertain, but the overall tension is so large. The answer Keir and Vivian give in the talk, the correct one, is that it's in the 2D plane, including the spectral index, where the tension is clear. But this confused me because ultimately, as they say at other times, the spectral index is a parameter that condenses a lot of the information. What is ultimately measured is the amplitude of the power spectrum at a bunch of different scales. And if that's so uncertain, surely there can't be that much tension, right? Because it can have any value and therefore it can fit the CMB value, it can move up and down. And looking at this plot, yeah, can I not just move the whole thing up and the measured data points lie happily on top of the Planck inferred values at the smaller scales? And at the larger scale, there's still this amplitude uncertainty, so where's the tension? That was my confusion, but I wasn't articulating it super well. But what resolves this is that the uncertainty in the amplitude is an overall uncertainty in the amplitude of the Lyman-α power spectrum, the eBOSS one. However, the relative amplitude of this power spectrum between the different scales must be known much more precisely. I don't know the physics behind that, but that must be the true statement. And therefore, the amplitude uncertainty is not an independent uncertainty from scale to scale, where each data point can be much higher or much lower, but an overall uncertainty that systematically shifts the whole plot up or down. However, wherever it shifts to, the relative change in amplitude from scale to scale is still more precisely known and must follow that particular slope. So once you realize this, it's clear why there's so much tension. Because yes, you could shift the whole data point up 1.5 sigma and it lies on top of the Planck prediction on the small scales. However, then your forced slope of the power spectrum will grossly overpredict the large scales measured by the CMB because it has to follow that slope. And the CMB is very, very well measured on CMB scales. If instead you even just shifted it up less, so that on the large scales, the CMB scales, the amplitude is on average correct, you'll still overpredict the very, very large scales and underpredict the smaller CMB scales. So not quite the small scale Lyman-α ones, but the small CMB scales. And again, these are very precisely measured by the CMB. So you might get one precise pivot scale correct, but everything smaller and everything larger you will get grossly wrong. And yeah, no matter what you choose for the normalization, the forced slope will always clash heavily with the CMB. In fact, you could even just throw away all the overall amplitude information, and I'm pretty sure there'd still be lots of tension. You can see it by eye in this plot. So if you were completely free to choose the best fit amplitude and pay no penalty for this in the Lyman-α likelihood, pretty sure you'd still get lots of tension just by knowing the relative between scales relative amplitudes. One thing I'd be super curious about from experts, and maybe there's someone watching this who can answer it, is what is the physical explanation for why the overall amplitude on the eBOSS scales from the Lyman-α is so uncertain, but the relative amplitude is so precise? That I don't know. And I'll let you get back to the main recording.
So these are the actual contours given. Lyman-α forest data is the black contour on this amplitude and spectral index at the small scale pivot. And then blue is the constraint from a combination of not just Planck CMB, but also the standard BAO and supernovae data under ΛCDM in blue. And this is where we measure the 5 sigma discrepancy. So explicitly, we measure that using the parameter difference posterior distribution, which is important when we consider the extended models. These posteriors become non-Gaussian, so we account for the tails in the distribution. And so you can see that if you integrated over n-lin, there would be essentially no discrepancy in delta lin. But that discrepancy is really being driven by the running in the power spectrum.
The definition of n-lin is what?
Is the spectral index at k of 1 h of a megaparsec. Although, let me be very explicit, it's defined in velocity units because the conversion from velocity to spatial units depends on the cosmological model in that it has a factor of h and omega m in there. So it's explicitly defined in the velocity units.
It must be different to the NS that Planck would normally quote, because that's scale independent in lambda CDM and it's like 0.96. So there must be some different definition here.
It's just a matter of definition. There is no problem in going to a definition where you could get numbers that look much closer to what we are used to, as long as you look at a different scale. And I fully agree with you that on paper, lambda CDM would predict at these scales. If we were to look at NS, the equivalent of NS at those scales, you would have found 0.96. It's scale independent. I agree with that. So here you would say that the tilt is smaller. The value of NS is smaller than 0.96.
Okay, but within lambda CDM, it doesn't matter what scale you measure this at, right? Because within lambda CDM, it's just one value. So if you measure it at one scale, by definition, it must be the same at all the other scales.
Yes, if there's not a tension. Yeah.
Okay, I think I get it. So why is NLN used? Does it make sort of physical sense in the Lyman-α context?
Well, it really is directly what is being measured. What is really being measured is the linear matter power spectrum and so this is defined at redshift 3. So it's really at the central point of where the data is sensitive to. You could project it to the small scale primordial power spectrum, and so in some of my previous work, that was in some of the emulators that we built, and I know that Simeon Bird put a paper out recently where he constrains with his students the amplitude and tilt of the primordial power spectrum, but defined at a small scale pivot that maps to the scales that the forest is probing.
And there you would still get this kind of 5 sigma-ish tension if you used exactly that. Okay. Well, it's been staring at us on the screen now for the last sort of few minutes where we've been discussing the perhaps most interesting part of the paper. So, Keir, I'll let you now talk about, running ultralight axions in warm dark matter, as I think you were about to.
Right, so precisely, so there's significant tension under lambda CDM. So of course we consider, in the letter we discuss possible sources of systematics, but also we ask what new physics would you require to reconcile these. And so the first thing we consider is neutrino masses. So this is traditionally one of the main sort of science drivers of these sorts of analyses, these 1D power spectrum forest analyses, because you're probing scales where you would be below the free streaming scale of the neutrino. And in particular, the hope is that in combining it with a large-scale pivot like the CMB, you could see the relative suppression that neutrinos would form. So the light blue is the Planck constraint, or Planck plus BO plus supernovae on neutrino masses. And the problem is that when you allow for suppression from neutrinos, it doesn't really change the tilt. You really do just get a step function suppression. And so neutrinos are essentially unable to produce the suppression and running that you need.
Maybe you could show, I don't know if it's easy to swap slides, but you could show what.
Exactly. So maybe go back to this plot, right? So each of these colored lines is the best fit linear matter power spectra for each of the extended models that we consider. The light blue is the neutrino, and you can see that it doesn't really, when you combine the data sets, it doesn't really fit either data set particularly well, because it's sort of trying to find a bit of the power spectrum where it gives you some running in the tilt, but then you kind of end up boosting the power quite a lot on larger scales. So it really doesn't work.
I was just going to say one thing that is important to say is that we're really talking about standard model neutrinos, so the temperature is fixed by standard model physics. We're not playing with that. Otherwise they would start looking like warm dark matter, obviously. And so there is a one-to-one correspondence between just the mass and the scale and the abundance of these objects. Now, once you fix the temperature, the Fermi-Dirac distribution. So that's why, you're forced to mess up the CMB if you try to adjust the right mass scale, essentially.
I mean, so the delta chi squared, you get a slight improvement of about 2 when you add the neutrino model relative to lambda CDM for the combined constraints. But the delta chi squared for the other models that we consider is of order 25, and you really get a perfect fit, a statistically consistent fit to both data sets.
Oh, certainly by eye you can kind of see that here.
You can see by eye, right? Yeah.
And it's important to say also, you get an improvement over lambda CDM in the combined analysis. But when you look at what's the residual fit to Planck, I mean, what actually is the fit, the chi-square of the CMB data that you get, or even the Lyman-α data that you get, is still terrible. Any sort of p-value test or any sort of test asking, is this a good fit, would tell you that it's not. Even if it's improving over LCDM slightly, you're not satisfied by it.
You mean with the neutrino mass?
With the neutrino mass, yes, exactly, with the neutrino mass.
There's potentially important consequence here, which means that any neutrino bounds quoted from a combination of CMB, BAO, supernovae, and eBOSS have residual tension within the bound.
Exactly. As Keir is saying, the point is that you end up, when you combine the two, the cosmology from which you're trying to interpret your bound is a bad fit too. It's a bad description of the universe. Like the ΛCDM plus neutrino mass is just, you're not just degrading a good fit and asking how much can I degrade a good fit and get in extracting a bound. You're in a very bad part of the parameter space and you're extracting a bound. So it's asking, it begs the question as to whether it's robust.
And so in green, we do the simplest thing, which is to actually allow some running in the power spectrum. And this is in the primordial power spectrum. So alpha S is defined as, I think it's the logarithmic derivative of the spectral index with K. And as you would expect, it works very well, right? If you have some running in the primordial power spectrum, you expect to see that at later times that the forest is sensitive to. So that's the green line. And so in particular, that reduces the tension to 0.92 sigma in the contours. So that's the green contours. And what we also consider is dark matter models. So these are also the first time that people have used eBOSS data to look at these mixed dark matter models. And I think that's because it wasn't appreciated that this compression holds for these mixed models. Of course, it doesn't hold when you have very strong suppression, but if you consider sort of subdominant fractions, then it is valid to do the analysis.
So in this analysis, you're presuming that the remaining dark matter is just utterly vanilla, pressureless, cold dark matter?
Yes, exactly, yeah. And so what you find is that there are configurations of the dark matter transfer function where importantly you can get this running in the tilt. So the yellow line is ultralight axion. If you move the bottom part of the step function, you can capture this running in the tilt here, and also fit the suppression in the power spectrum very well at the same time. And so at the level of contours, for warm dark matter, it comes down to a 1.63 sigma discrepancy, and for ultralight axions, 0.56 sigma.
My Chi by I thinks the warm dark matter and the running should have the opposite values, but Chi by I is notorious for making mistakes, I guess.
Yeah, so I think the actual chi squared is better for warm dark matter, but for the posterior, once you've marginalized over other parameters, that the projection into this plane gives the tensions that we quote.
Okay, so it does have some mild effects on other observables in some way or another, other parameters.
Well, in particular, so these open contours here are the constraints on these models given the large-scale data, and so they have a large amount of parameter space that is essentially unconstrained. And so, in these contours, I'm integrating over the mass and the fraction of warm dark matter. And so I think what happens is that given Planck, there's more posterior weight at CDM-like fractions and masses of warm dark matter, which once you integrate over that volume, builds up posterior around the Planck values of delta lin, n lin. But there is a tail that's certainly consistent with the Lyman-α forest data.
Yeah, in other words, if we had fixed the warm dark matter mass and only played with the fraction, the warm dark matter would have shown a much tighter degeneracy, which our estimator of tension would have liked more. But because you're marginalizing over all possible masses, then you're getting that in the whole parameter space, the tension is larger.
Yeah. It's certainly possible that the best fit value can be better for one model, but the total volume of that model can have more stuff that's a bad fit.
And I suppose it's worth saying that although we consider these dark matter models, we do vary for each of those two parameters rather than only one parameter for the running. And so we don't do an explicit model comparison exercise, but one may favor the running simply because it has one fewer parameter than the others. So I guess just to come back to this point of why retention was missed before, we have this panel in the paper, which is the constraints on NS and sigma 8, the colored contours given combination of CMB, BO, and supernovae for different models. And then in gray is the constraint given Lyman-α forest data alone. And you can see that it's huge. And that's partly because, I mean, it's really, this particular case is being driven by the fact that we're trying to constrain 6 parameters from essentially 2 data points. So, this is using the compressed likelihood, and as you would absolutely expect, you're unable to constrain 6 parameters simultaneously with 2 data points. What is done is typically to put some priors on some parameters. So in particular, you fix things like the baryon density, you put a prior on the Hubble parameter, and you can extract, using those priors, you can get tighter constraints on NS and sigma 8. But these are not in discrepancy, or there's a mild discrepancy as quoted in the Planck paper that Vivian talked about in the standard parameters.
It's the x-axis that's the problem here, though, right? Like if you were to still have the value of the matter power spectrum at the pivot of the Lyman-α results, you'd still reconstruct that 5 sigma tension, right? Because NS has to be the same over all scales. So saying NS or NLin or whatever you want to define it at whatever scale.
I think you're right that the central value has to be consistent, but I think the statement that the error bar inflates when you project to a different pivot holds true.
Okay. I'll believe you. It'll probably take me a bit longer to conceptually understand that, but that sounds plausible. Okay, thanks.
Okay, so then you can actually see what are the full joint constraints on these extended parameter models. So we get a constraint on alpha S. So here I'm showing the marginalized posterior on alpha S, delta lin, and the color shows the value of n lin. And as you expect, as you increase the amount of runnings and more negative values of alpha S, you get some suppression, but in particular you get low values of n lin. And this is actually quite a significant preference for running, sort of order 5 sigma, preference for running in the power spectrum. We don't really, in the paper yet, consider implications of the particular value of alpha S. It is of order of magnitude larger than the values you expect from just slow roll inflation, for example.
I think it's fair to say that this would, you could never really fully rule out single field slow roll inflation, I guess, so simply, but yeah, it's not what you expect from single field slow roll. As Keir is saying, it's 1 order of magnitude, so it would have important implication for model builders of inflation.
And so then we also consider these dark matter models. So here I'm showing ultralight axions on the left, warm dark matter on the right, and I'm showing the degeneracy with delta lin. And so for ultralight axions, you get a preference for a non-zero contribution. We restrict ourselves to no more than 5% of the dark matter. So these are certainly subdominant contributions. And it goes from this ultralight regime of 10 to the minus 26, 10 to the minus 24 eV. So you have large debris wavelengths, on the order of several megaparsecs. And it has this interesting W shape. And what's happening there is that as you make the axion heavier, the debris wavelength gets smaller. And so the amount of suppression you gets less. And so delta lin gets higher. I should really put these on the same slide. So on the left here, I show the degeneracy with n lin. And what you see here is that as you vary the fraction, you're essentially moving, you're fixing the scale, but you're moving that transfer function up and down. And so you're picking the bit of the transfer function where you're just getting the curvature to match the amount of running in the spectral index that you want. And then for warm dark matter, we again see a preference for a non-zero contribution on the order of sort of 10 to 100 EV, but of order 2 to 5% of the dark matter. And again, you see the same effect, that as you increase the warm dark matter mass, the particle becomes more CDM-like, the free streaming scale becomes smaller, but again, you can sort of vary the fraction to move the transfer function to give you the right spectral index. So those are the constraints on new parameters. And of course, in the letter, you have to consider what else may be causing this discrepancy. And so we don't do a detailed analysis in this piece of work, but we consider things like systematic effects. And so in particular, we talk about the effects of high column density absorbers. So what happens when you analyze Lyman-α forest spectra is that you don't just see the absorption from around mean density IgN gas, but you also see absorption from high column density absorbing systems. So that's damp Lyman-α absorbers and Lyman limit systems. These are self-shielded clouds of neutral hydrogen gas. And that means that the neutral gas is shielded in the center, and you get a significant broadening in the absorption with a Voigt profile. And in the analysis of eBOSS, they run detection algorithms at the spectra, so at the quasar spectra. They look for these broadened absorption lines, and when they detect them, they remove them. So you actually have saturated absorption at the center of the profile, and they correct for the Voigt profile in the wings. But there's always a residual contamination. The Lyman limit systems, which are the less dense, high column density systems, they will remain. And if you have noisier spectra, it becomes harder to detect these systems. And so what you do is you marginalize over residual contamination of high column density absorbers. And you can measure the effects of these from hydrodynamical simulations. You know that this will change the spectral index that you infer. And so, but they do marginalize over a contribution, and they find that the fit to the data doesn't improve when they include a template for this residual contamination. But we discussed that perhaps, in particular with a view to the data that's coming, DESI is happening, has already released data that, further improving systematics like high column density absorbers will be important in distinguishing the source of the tension that we've measured.
Cool, that's interesting. So yeah, where to next, both for you and for how the community should change based on your results? I guess partially it would be interesting to look into what might be causing this from an observational perspective, but then also if this evidence of warm dark matter or axion dark matter or running is evidence of that type of new physics, where else should we look to see and to distinguish between perhaps the three different candidates?
So I think we need to always improve our modeling of the intergalactic gas, effects like high column density absorbers, the effect of AGN feedback on these spectra, potentially relating to the S8 tension, right? That we know that feedback can be strong, that more recent hydrodynamical simulations have shown that feedback can be strong, that this can back react on the matter distribution, it can affect the matter power spectrum. And we know that the feedback is also the first order heating the gas where we observe the Lyman-α absorption. So we, again, in the constraints that we use, we're marginalizing over an effect of AGN feedback, but we want to update those templates again, given improvements in the hydrodynamical modeling.
So you said earlier on that this is on the more linear scales. Why would we then worry, and it's at a higher redshift, is it still true that we worry about these baryonic effects at these higher redshifts?
I mean, certainly these high column density absorbers exist in large numbers. There's quite a large population at high redshift, simply because the neutral fraction, I think it's slightly higher at redshift. It's actually very small, the neutral fraction, but you actually only need a very small neutral fraction to cause an observable signal. Things like feedback are important. You do see AGN, at redshifts 2 and 3, where we make these observations, and they can have large jets of order megaparsec in scale. So these are certainly effects that you need to account for when simulating the gas. So I think the other thing is to sort of bring other pieces of information in here. So these Lyman-α forest observations with eBOSS are relatively low resolution, the sort of medium resolution are on the order of sort of 60 to 70, I think. But we do have other data sets where we have much higher resolution observations of the Lyman-α forest. And as I was talking about earlier, spectral resolution equates to spatial resolution of the dark matter distribution along the line of sight. And so there are well-studied sets of these high-resolution spectra from the Mike and high-res spectrographs in particular, also the UVES spectrograph on the VLT. But the number of spectra we have are much smaller. So we're talking rather than hundreds of thousands of order tens of these spectra. So the statistical error bar is much larger, but the maximum K to which you can probe and model is much higher. And so certainly if you have suppression or running in the power spectrum in eBOSS, you would expect to therefore see deviation from ΛCDM at smaller scales. So, and this may be a way to distinguish new physics sources that if you take these best fit models, extrapolate to K of 10, and so these high resolution data sets probe of order K of 10 and higher, you will see that there's significant deviations in these transfer functions at high K, in particular in the spectral index that you would expect to see. And so I think combining eBOSS with high resolution data is important, and also other small scale structure probes like Milky Way substructure. These are all probes of the high K power spectrum. We want to see consistency all the way from gigaparsec scales in the CMB down to sub-megaparsec scales in small scale structure. And then finally, we talked about at the beginning a motivation being that we want to see what Lyman-α forest sheds, how it sheds light on the S8 issue. We did do some analysis of trying to fold in the weak lensing information using an S8 prior. I think it's fair to say, and Vivian can say more, that we didn't particularly find that essentially the amount of suppression that eBOSS wants is slightly less than what the S8 tension seems to suggest. But what we think we strongly feel is that the central argument here that you have to assess consistency at the scales in redshift at which you have information content applies also to the weak lensing experiments. And I think there's been some work demonstrating that it may not be that 8 megaparsecs is the scale at which the discrepancy between weak lensing and CMB is actually manifesting. That we know that the weak lensing analyses are sensitive to highly nonlinear scales up to K of 1 in those megaparsec, and that actually the discrepancy may be happening at smaller scales than to what sigma rate is sensitive, that you have to, again, do this projection of information to project to the parameters that we're used to using. And so what we really think that the community needs to do is assess consistency through parameterizations that capture information content in a given experiment. But that this becomes slightly non-trivial in that, for example, if you want to consider the effect of axions on small scales in the weak lensing experiments, they are very sensitive to nonlinear effects. And notwithstanding uncertainty in nonlinearities in the CDM model, we're still trying to understand the effects of axions in the nonlinear regime, where you have to account for interference fringes and these sorts of effects.
And all of the high-powered emulators and everything haven't been made with axions in mind, I see.
Yes, it's a harder problem on the simulation side because solving the Schrödinger-Poisson equations is computationally expensive. So running full simulations to low redshift and high resolution is essentially unfeasible computationally. But I and Vivian and others have been working on sort of semi-analytic approaches to try to tackle this problem, like using halo models to try and make headway.
We have not shown explicitly S8 in this talk, but it's clear that the S8 value, when you compare them, the S8 predicted from these models in very good agreement with Planck, with lambda CDM, in fact. But it doesn't mean that this could not be also at the origin of some discrepancy that we see in the weak lensing data. I just wanted to be very clear about this. This is really one of the key points, I think, of what we're doing, is that you need to compare things at the relevant scales, and in order to draw robust conclusions as to whether the new physics models that you're looking into are solutions or not of these tensions.
Yeah, actually, another question that's just jumped into my mind, based on what Keir was saying, that, okay, you don't know how the non-linear stuff will happen, especially in like an axion dark matter sort of thing. Is there reason to speculate or believe that they'll compound each other, and that somehow the existence of baryons and axions will coexist to amplify, like it won't just be 2 times what it was with them isolated, it'll be much more? Is there some reason to speculate that?
This is something that I've been thinking about, that precisely the effective feedback will be dark matter model dependent. I mean, we know already that it certainly affects the timing and duration of structure formation so first order, if you have some small scale suppression, you will delay the onset of early time structure formation. I think it's uncertain, like the extent that then propagates the later times and the strength of feedback processes that come. But I think it's highly non-trivial, certainly. Like this feedback is coming through some oscillating dark matter potential. There could be some non-trivial effects, yeah.
There was this interesting paper, and there was a cosmology talk on it earlier this year on peculiar velocities that seemed to be having like a similar suppression in power at the very late redshifts. But I guess because it's the peculiar velocities, it's also quite small scales because it has to be relatively local. Is there any possibility that it's warm dark matter or ultralight dark matter causing what they're seeing with the peculiar velocities? Because they're parameterizing it by like a modification of gravity at the very late times. But
yes, from what I remember of the paper, what they're looking at is a modification of the growth rate. They're parameterizing that would affect all scales in the same way. So it would lead to some sort of scale independent power suppression. And then as far as the peculiar velocity data themselves are concerned, I don't know exactly what scales that they are probing exactly. If they are probing, so here I'm just going to make an educated. If they are indeed probing small scales, then yes, they are going in the same direction. From what I remember of the paper, they were also interpreting some of the anomalies in Planck as a hint of new physics, as a hint of a deviation for the growth rates from ΛCDM, and that we would not be explaining because, of course, the ΛCDM, the large scales, is completely unaffected in these games. So here we're really decoupling small scales and large scales. So it's not exactly the same effect. It would need to be tested explicitly, but maybe it would work for peculiar velocity, but it would certainly not work for what we call LNs, for instance. Yeah.
do you guys have anything else you want to say before we wrap up?
One thing that I would like to add, because we've been criticizing neutrino mass constraints, and I don't want people to start thinking, whoa, we can't believe in the neutrino mass constraints. So the one thing that I want to add first is that the most robust neutrino mass constraints, they come from purely CMB, BAO, so purely background effects, in fact. There's some lensing effect inside of the CMB, and then it's just effect on the angular diameter distance within the BAO. And these already are very strong, limiting below something like 0.2, maybe even more than that from the latest data release. I forgot the exact number. Then, as far as eBOSS is concerned, what we have checked is that even when we include the running of the tilt as an extra parameter, in fact, the neutrino mass constraints stay fairly robust. They relax only to something like 0.11 EV compared to 0.09 or something like this. So it's not like suddenly neutrino masses became perfectly, became completely removed or whatever. So I want to say that, sometimes even though it looked like things are not robust, when you do the exercise in practice, it's still fine. So yeah.
And maybe we should say the DESI is happening, and they already have of order tens of thousands of spectra. They expect to have of order a million spectra, so at least a factor of 5 improvements. And so we're going to have follow-ups to this quite soon, I think.
Awesome. Well, okay, last question. What work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the community?
I had a paper in mind that is sort of some collaborators of mine. So there's this paper, Glimmers from the Axiverse. This is more my side project, and sort of you're interested in these axion models and connecting them to high energy theory directly. So can you use sort of astrophysical constraints on the population of axions contributing to dark matter? Can you relate that to actual concrete models that produce these? And so there's some cool work. The lead author is Naomi Gendler, where they start to take these sort of databases so this is in string theory, these databases of Calabi-Yau manifolds, and actually calculate the spectrum of axion masses and decay constants that you would expect to have, and actually starting to sort of draw a connection between the constraints that we're doing with data here to the landscape of Calabi-Yau manifolds. And so there was a first paper called Glimmers, and I'm personally interested in like following up on that and sort of starting to understand the connection between data and theory.
So one thing that maybe I wanted to add that is actually interesting in someone not overlooked by the community and connected to what we've talked today about, are also hints of some sort of new physics inside of the higher resolution Lyman-α data that we've mentioned, that Keir has mentioned, and that also seem to indicate a change in the tilt and the amplitude of the spectrum that could, and so the paper that I have in mind in particular was written by Diana Hooper and Matteo Luca, and looked at a specific model of dark matter neutrino interactions in order to explain this sort of effect, but maybe very well connected to what we're seeing here. Yeah, if we were to do combined analysis, and in principle we have the tools to do that, and it's something that Keir and I are very excited to look into. Yeah.
All right, thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, as YouTube will know to recommend more stuff like this to you, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, it might be a good idea to check out Keir's earlier talk, which was also looking at kind of these axion dark matter models. I think he even showed a plot from that paper and talk earlier in this talk. But yeah, I guess constraining them on different scales. And there was one thing, I'm going to interrupt my outro just to ask Keir a question. There's one thing I had intended to ask you about in this talk. You did find a hint of evidence in that earlier analysis for a particular mass of axion in a particular fraction. I presume that is kind of consistent with where you're finding evidence here now. How does that relate to you saying that the S8 tension kind of isn't impacted very much by your newer stuff here today?
The mass scale is roughly the same, so it's of order 10 to the minus 25 EV axion, but it's precisely that you need sort of slightly more axions to lower sigma 8 than what we find to lower the delta effective and effective. But I do return to the statement that if you actually, like, the limitation in what we did before is considering only its effect on sigma 8 rather than the direct fit to the small scale lensing data.
And if you took that value from that earlier work here, it would be, do you know off the top of your head how many sigma good fit kind of thing it would be? Would it be way worse than, I mean, you've got your kind of 0.5 sigma tension, obviously that's not tension at all for your best fit value, but would it be still a nice-ish fit, or would it be way off?
I'm actually not sure, but Vivian did run the chain that looked at this.
Okay, cool. No problem. Yeah, go watch that talk, and thanks Keir and Vivian for the great talk.
Thanks, Sean.
No, thank you, Keir, for that, and thank you, Sean, for having us. It was awesome.